All right, everyone, welcome to this video. This is a very interesting problem involving relative humidity. So if you watch the weather report or you have a weather monitoring device, you might see the readout of the relative humidity, and maybe you've always wondered what that was actually telling you, especially the curious case of when it reads 100% relative humidity, I remember when I was young, I used to wonder if that meant like you're underwater, there's 100% humidity. Well, of course, that's not true. That's just a little joke. But in this problem, we're going to be looking at the air in a room that is at a certain amount of relative humidity and actually try to calculate how many grams of water that actually corresponds to that is dissolved in the air. So let's begin with the actual definition of relative humidity. We have a certain volume here, and we have some molecules of water that are dissolved in the air. And so the relative humidity, or the RH, is going to be given as a ratio of the actual partial pressure of water. So I'll write that as pH2O, divided by the saturated partial pressure of water. I'll put pH2O sat for saturated. So, and this could be expressed as a percent if you do times 100. So suppose we had a case where the relative humidity was given as 75%, which is fairly high, and we had that the saturated vapor pressure of water is going to be 3.17 times 10 to the third pascals. And let's assume that that is at the temperature of the room, which is going to be at 32 degrees Celsius. Okay, so we should also note that eventually if we want to get the mass of the water, we're going to need to know the number of molecules, and that's ultimately going to be back to the ideal gas law, in which case we're going to need this temperature in in Kelvin. So what we need to do is add 273 to this number, and we'll have temperature equal to 305 Kelvin. So let's just have that ready. Okay. So the first thing that we can do is use our relative humidity equation to try to calculate what is the pressure, the partial pressure of the molecules of water. So that's the pH2O. So essentially, if we just take the relative humidity and multiply it by the saturated vapor pressure, we will get the actual vapor pressure. And to make this work, since I defined the RH with the times 100, I'm just going to have to throw in a divide by 100 here, because what I want is the relative humidity fraction, not the percent. So I'm going to throw that in there. Okay, so we can do this now. It's going to be 75% divided by 100. And the saturated vapor pressure is 3.17 times 10 to the third pascals. And that will be the vapor pressure of the water. So you can multiply that out and you will get basically 2.38 times 10 to the third pascals as the actual vapor pressure of the water. All right, now that we have that, we can proceed to using the ideal gas law to try to work out how many actual molecules are in the gas. So we can assume that we have a room with dimensions, certain dimensions here. I'm just going to make this a little bit 3D. So we have a length, we have a width, and a height. All right, and the volume of that room is of course going to be equal to the product of those three numbers. So we could just go ahead and compute that volume. Let's just say we're doing 3 meters times 4 meters times 2.4 meters. So that will come out to be 28.8 meters cubed. And that'll be our volume. And to now go on to the ideal gas law, we're going to have PV equals NKT. And for that, we can try to solve for N, because once we know the number of molecules, then we can use the molar mass of the gas of the water to figure out what is the total mass. So let's just divide both sides by kT. PV over kT will be equal to N. And now we can start plugging in our numbers. So the pressure is going in, is the one that we computed for the vapor pressure, 2.38 times 10 to the third pascals. The volume is going in as 28.8 cubic meters. We have Boltzmann's constant for K, 1.38 times 10 to the minus 23rd joules per Kelvin. And then the temperature in Kelvin back from the top, the 305 Kelvin. Okay, and that should be the number of molecules. We can do that math. And this is going to come out to 1.63 times 10 to the 25 molecules for N. But what we want was the total mass. So we just need to do, remember our chemistry, that water is H2O. And hydrogen is, of course, 1 gram per mole. Hydrogen is 1 gram per mole. And oxygen is 16 grams per mole. So if you add that all up, H2O is going to be 18 grams per mole. Well, let's just start another column over here. 18 grams in 1 mole can be converted with Avogadro's number to per molecule. So I'll put in 6.02 times 10 to the 23rd in the denominator here. And that's molecules. So I could divide that out and it would get me the grams per molecule. So that's going to be 2.99 times 10 to the negative 23 grams per molecule. And now that I have that, and I have over here the number of molecules, I'll just multiply these results together. So 2.99 times 10 to the minus 23rd grams per molecule times the number of molecules that I have, which is 1.63 times 10 to the 25 molecules. And that will come out to be about 487 grams. So 487 grams, almost half of a kilogram of water is actually dissolved in a room of this size when you're at 75% relative humidity. I thought that was a surprisingly large number because you can't actually feel the humidity. Well, you can feel it on your skin, but it's dissolved in the air. You don't actually see the liquid, but actually it's quite a large amount of water. And if you were to use an air conditioner or a dehumidifier, you could imagine that the little drain cup on that device is going to fill up because there's actually quite a bit of water dissolved in the air. All right, thanks very much for watching, guys, and I'll see you in the next video. Bye-bye.